So we're going to take a closer look at the difference between absolute extrema and your relative extrema, and what some of the differences are when we're using calculus to try to find these values. So when it comes to the relative extrema, you have to have the condition of switching from an increasing to decreasing or decreasing to increasing part of your function. So in the graphs that are illustrated here, we're switching from increasing to decreasing right about there, decreasing to increasing there, increasing to decreasing, and again, decreasing to increasing one more time. So we have 4 relative extrema in that first graph. In the second one, you can notice that we're going to increase, 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 and we're going to continue to increase until we get to the top here. So there is another local max or relative max. And it's going to continue to decrease, and there is a value that's right here that kind of looks like it evens off, but we're going to continue to decrease, and so we end up with another local min down there at the bottom. So only 2 relative extrema in that second graph. Your absolute mins and maxes, though, aren't necessarily going to be at those same mins and maxes we found that were local. So for example, in this very first graph, if we look at the absolute min that's in here, it's actually down here located at an endpoint. The absolute maximum value occurs in 2 places. It occurs at the same local max that we have here at x equals 1, and also happens over at x equals 9 at the endpoint. So the absolute max for this is still 5, and it occurs at 2 different locations. The absolute min for this is a -7, and it occurs at an endpoint. For your absolute mins and maxes for their second graph on the right-hand side, we do have an absolute max that happens to be the same as the as the local max up there at x equals -1. It has a value of 6. But when you consider your minimum, this local minimum has a value of -4. But if you look at this endpoint, it's approaching a -5. So technically speaking, the second graph does not have an absolute minimum value. And the reason is because we are approaching -5, but we never quite get there. And the function continues to move closer and closer to -5. It goes to -4.9, 4.99, 4.999. It continues to get closer and closer. And no matter when you think that you stop, we can always keep going, and we never actually reach -5. So to sum up kind of your absolute extrema and how we would kind of write this, we were going to say that your absolute max of this function is going to be a value of 5. And when we talk about values, we're referring to y values. We were also going to be a little bit more specific and say that the absolute max is 5 at x equals 1 and x equals 9. So that's how we point out the 2 locations, the x values, of where this absolute max occurs. We're also going to say that the absolute min value for this function is a -7. And it happens at x equals -9. For the graph on the side, we're going to say that our absolute max is a value of 6, and it happens at x equals -1. And we're going to say that there is no absolute minimum. Now, the reason that we are structuring absolute maxes and mins in this phrase is because when we talk about absolute extrema, we're really focused on that y value. That's really the most important part of this. So we're really just trying to highlight what that y value is for these absolute or for these extreme values that we have. The location of where those are located, or the domain part of where those maxes and mins are located, is kind of a second thought when it comes to absolute. So when we try to find this analytically, meaning we're not given a graph and we have to use our equation and our knowledge of calculus to try to find absolute extrema, we need to consider a couple of different options. We first need to consider our critical values. So the critical values occur where our derivative could be 0, as in all of these local extrema. Our critical values include when we have a derivative that does not exist. such as those two values on the other graph. And we got some derivatives of 0 over here. But as also illustrated by that first graph, we had absolute extremas occur at endpoints as well. So not only do we have to consider our critical values, but we have to consider our endpoints, because those might be absolute maxes too. So since absolute extrema may occur at endpoints, we do not always need to focus on your derivatives switching from negative to positive or positive to negative, the same way we did the local or the relative mins and maxes. Instead, we need to consider all those critical points, no matter if they're switching from increasing to increasing, decreasing to decreasing, or if they are possible endpoints. So all critical points and all endpoints are fair game to be an absolute max or min. What we're going to do is we're going to compare what the different values are for each one of those critical points and each one of those endpoints. And just by making a simple table, we can compare them and say which one is the highest y value and which one's the smallest y value. Here are the steps for what we're going to do with this. Finding your absolute extrema. Step 1, we're going to find the critical values of f. This is where your calculus comes into play. Finding your critical values is the exact same as it was finding your first derivative test. So we're going to take our derivative, f prime, we're going to set it equal to 0, set it equal to does not exist, and we're going to figure out where those critical values are. Now, step number 2 and number 3 are going to go hand in hand. We're going to substitute each critical value back into f, and we're going to plug each endpoint into f. And we're going to make a simple table to illustrate all of those different values we're plugging back in, and we're basically just going to compare their y values. So even though we're going to use calculus for step number 1, we're not going to say where are we increasing and where are we decreasing. We're literally just taking all of those critical values that we found, and we're going to use them all in addition to the endpoints. Our last step is to report back the absolute minimum and maximum y values that we find. They may, in certain directions, specify where is the x value location of an absolute min or max, but typically when they're asking for an absolute extrema, they want the y values. And this is why we're going to phrase it as the absolute max is 5 at a certain location. So we're going to use that phrasing anytime we report back our results. So we're going to take a look at a couple of problems where we're going to find our absolute extrema. So you'll notice over here they do give us our closed interval, so those are our 2 endpoints that we are going to need to check in addition to all of our critical values. So our first step is to find f prime, and we're going to set that equal to 0 and does not exist. So here we're going to use the quotient rule to take our first derivative. We're going to simplify the numerator a little bit. We end up with a numerator of 2x and a denominator of x squared plus 1 squared. When I set our first derivative equal to 0, we come up with a critical value of 0. When we set the first derivative equal to does not exist, we actually have no solutions because the denominator will always be a positive number and we will never reach 0. So our next task is to set up an XY table with our endpoints and our critical values in here. So our endpoints are going to be -2 and 1. Our critical value is going to be 0. And we're going to plug each one of these values into f of x to find out what the y values are going to be. So we're going to find f of -2 and we end up with 4/5. We're going to find f of 1 and end up with 1/2. And then we find f of 0 and we end up with 0. So out of all of these amounts that we found, all these y values, we can see that 4/5 is going to be the largest y value and 0 is going to be the smallest y value. So we're going to report back these results. The absolute maximum value is 4/5 at x equals -2. The absolute minimum value is 0 at x equals 0. And that's how we will report back our results. Take a moment to pause and try the next problem out on your own. So after taking the derivative and setting it equal to 0, we come up with a trig equation we're trying to solve that ends up being cosine of 2x equals sine of 2x. And if you think about your unit circle, what you're essentially trying to find is where is the cosine value and the sine value going to be the same. And if you think on the unit circle how cosine is represented by your x-coordinates and sine is represented by your y-coordinates, you're essentially looking for the points that are on that line of y is equal to x. And that is occurring at the angle of pi over 4 as well as a 5 pi over 4. Now, because this is cosine of 2x and sine of 2x, remember that 2x is going to be your pi over 4, and 2x is going to be your 5 pi over 4. So when solving for this, we come up with pi over 8 and 5 pi over 8. Now we do have to consider that we are restricted in our domain here. We're only looking from 0 to pi over 2. So that means that pi over 8 is the only critical value we're really interested in, because 5 pi over 8 is a little bit greater than pi over 2. So the next thing we're going to do is set up your table and compare your y values. So after we've completed our xy table, we will notice that the largest value that we have is going to be the square root of 2, and the smallest value is going to be -1. So we're going to summarize our results using the appropriate way of describing absolute mins and maxes.